Imagine sitting inside an airliner at 40,000 feet. Outside your window, the temperature has plunged to nearly minus 60 degrees Celsius, cold enough to freeze exposed skin in seconds. Yet just a few centimeters away, you're comfortable, breathing normally, watching clouds drift beneath you. Think about this. The small transparent panel beside your seat quietly withstands forces that could tear ordinary glass apart in an instant. Most people never think about this, but aircraft windows rank among the most heavily engineered, transparent structures on Earth. They survive pressure differences that push outward with thousands of pounds of force every single flight. They endure brutal UV radiation, hail impacts, vibration, and repeated expansion and contraction through thousands of takeoffs and landings. And this is where it gets truly extraordinary. One tiny defect, almost invisible to the human eye, can cause an entire window assembly to fail inspection. But here's what nobody tells you. Aircraft windows are not made from ordinary glass. In fact, many passenger windows rely on multiple layers of specially engineered acrylic materials, each designed for a different job. One layer carries the pressure load. Another acts as a backup. Another helps control moisture and visibility. Together, they form a transparent shield trusted with millions of lives every day. What happens next surprised even experienced engineers when modern aviation first demanded larger windows, higher altitudes, and greater safety margins. Manufacturers had to invent entirely new production methods capable of creating flawless transparency while maintaining incredible strength. The result is a manufacturing process that combines mining, chemistry, precision machining, robotics, and human craftsmanship at levels few people ever see. And our journey begins far from any airport, deep beneath the surface of the Earth. Every aircraft window starts with raw materials that travel thousands of kilometers before reaching an aerospace factory. One of the most important ingredients comes from natural gas and petroleum feedstocks that eventually become acrylic polymers. These hydrocarbons often originate in energy-producing regions across the United States, the Middle East, and parts of Europe. Long before anyone sees a crystal-clear aircraft window, the journey begins as molecules buried deep underground. Inside chemical processing plants, engineers convert these raw hydrocarbons into methyl methacrylate, the building block of aerospace-grade acrylic. Purity matters enormously. Manufacturers often target purity levels above 99.9% because even tiny contaminants can distort visibility or weaken structural performance. Imagine producing a material so clear that pilots and passengers trust it while flying through storms at nearly the speed of sound. The supply chain stretches across oceans. Specialized chemicals travel by tanker ships, rail cars, and sealed transport containers to aerospace suppliers. A single batch may cover more than 10,000 kilometers before reaching its destination. Most people never think about this, but one aircraft window can represent materials, labor, and logistics from multiple continents before manufacturing even begins. Then comes one of the hidden costs of aviation manufacturing. Producing aerospace-grade, transparent materials consumes large amounts of energy for refining, purification, and quality control. Companies invest heavily in recycling systems, emissions reduction technology, and waste recovery processes to reduce environmental impact. Yet the industry accepts these costs because failure is simply not an option when human lives depend on every component. And just when the raw materials finally arrive at the factory, their transformation is only beginning. What looks like a simple transparent sheet will soon face intense heat, enormous pressure, microscopic inspections, and manufacturing tolerances measured in fractions of a millimeter. The next stage turns chemistry into something capable of surviving the edge of the stratosphere. And this is where the real engineering begins. The moment the raw material enters the factory, the atmosphere changes completely. Towering production lines hum day and night as aerospace-grade acrylic pellets move through sealed handling systems. Every batch receives a unique tracking code, because manufacturers must trace each window back to its exact material source. Imagine knowing the history of every molecule before it ever reaches an airplane. First, the pellets enter drying chambers. Moisture is the enemy here. Engineers heat the material to roughly 80 degrees Celsius or 176 degrees Fahrenheit for several hours, while powerful air circulation systems remove microscopic traces of water. If moisture remains trapped inside the material, tiny bubbles can appear later and ruin an entire production run worth thousands of dollars. Next comes polymer casting. Liquid acrylic material flows into precision molds under tightly controlled conditions. Temperatures typically range between 50 degrees Celsius and 90 degrees Celsius, while technicians monitor viscosity, pressure, and chemical stability around the clock. The liquid slowly transforms into a solid transparent sheet through a carefully managed polymerization reaction. What looks simple from the outside demands incredible precision behind the scenes. The curing stage can take many hours. Massive ovens maintain temperatures between 70 degrees Celsius and 120 degrees Celsius, or 158 degrees Fahrenheit to 248 degrees Fahrenheit, allowing internal stresses to relax gradually. The air smells faintly chemical and warm. Cooling too quickly could create invisible weaknesses that may only appear years later after thousands of flight cycles. Most people never think about this, but patience is one of the most important tools in the factory. Once cured, giant CNC cutting machines take over. Diamond-coated tools spin at several thousand RPM, while computer-controlled systems shape each panel within extremely tight tolerances. The sound echoes through the facility like a high-pitched mechanical orchestra. Tiny transparent chips scatter away as machines carve components that must fit perfectly into aircraft fuselages traveling hundreds of miles per hour. Then comes thermoforming, one of the most dramatic stages in the entire process. Flat sheets enter specialized ovens and heat to approximately 150 degrees Celsius to 180 degrees Celsius, or 302 degrees Fahrenheit to 356 degrees Fahrenheit. The material softens and becomes flexible. Powerful forming equipment presses or draws the sheet into complex curved shapes that match the contours of modern aircraft fuselages. What happens next surprised even experienced engineers when first witnessed it. As the material cools, it remembers its new geometry permanently. Engineers carefully control cooling rates to prevent distortion. Laser measurement systems immediately verify dimensions to fractions of a millimeter. One small deviation can trigger rejection because every window must perform flawlessly under cabin pressure loads reaching several psi above the outside atmosphere during flight. Now comes polishing. Robotic finishing systems and skilled technicians remove microscopic surface imperfections until the transparency becomes nearly flawless. Bright inspection lights reveal defects invisible under normal conditions. The surface must remain smooth enough to minimize optical distortion while preserving structural integrity. Under these lights, even a scratch thinner than a human hair can stand out dramatically. The individual layers then move into assembly. Aircraft passenger windows usually contain multiple panes separated by carefully engineered air spaces. Specialized bonding systems align the layers with remarkable precision. Workers wearing cleanroom garments inspect every edge, every surface, and every seal because even tiny contamination particles can compromise performance. And this is where it gets truly extraordinary. Before any window reaches an airplane, engineers deliberately try to destroy it. They expose samples to extreme temperatures, pressure cycles, vibration, ultraviolet radiation, and impact simulations. Components that survive move forward. Those that fail reveal weaknesses before passengers ever step on board. But the most advanced testing system in the factory isn't a machine at all, and that's the mystery waiting in the next stage. By the time an aircraft window reaches quality control, it has already traveled through some of the most precise manufacturing systems on Earth. But here's what nobody tells you. The factory still assumes every window might contain a hidden flaw. That's why inspection often takes almost as much effort as production itself. In aerospace manufacturing, trust is never enough. Every component must prove itself. The first line of defense comes from advanced laser scanning systems. Red laser beams sweep across every surface, collecting millions of measurement points in minutes. These systems detect dimensional variations smaller than 0.1 millimeters, often far beyond what the human eye can see. As the scanners move silently across the transparent surface, computers build a digital twin of every window in real time. Then artificial intelligence takes over. High-resolution machine vision cameras capture images from dozens of angles under carefully controlled lighting conditions. AI systems compare each window against thousands of known defect patterns, searching for scratches, bubbles, distortions, contamination, and microscopic inclusions. What would take a human inspector hours can happen in seconds. Yet even these powerful systems aren't perfect. Most aerospace manufacturers target rejection rates below a few percent, but achieving that number requires relentless discipline. A tiny air bubble, a microscopic crack, or a slight optical distortion can trigger rejection. Imagine discarding a component that looks flawless to almost everyone on Earth. That's exactly what happens every day in facilities where safety always outweighs cost. Now comes the pressure test. Specialized chambers simulate the enormous pressure differences experienced during flight. Engineers repeatedly cycle the windows between low-pressure and high-pressure environments, recreating years of service within days. The chambers groan, pumps roar, and sensors record every microscopic movement. What happens next surprised even experienced engineers when these systems first revealed hidden weaknesses inside seemingly perfect components. But pressure is only the beginning. Test laboratories expose windows to temperature swings ranging from approximately minus 55 degrees Celsius to over 70 degrees Celsius. They bombard surfaces with ultraviolet radiation that simulates years of sunlight exposure. Some facilities even fire specially designed projectiles to mimic debris and hail impacts. Engineers intentionally create the harshest conditions imaginable because real skies can be even less forgiving. Every measurement must meet strict aerospace certification standards. Tolerances often fall within fractions of a millimeter, while optical quality requirements remain equally demanding. The window must not only survive extreme conditions, it must also allow pilots and passengers to see clearly through changing light, weather, and altitude conditions. Strength means nothing if visibility suffers. And this is where human skill still beats machines. Veteran inspectors stand beneath powerful lights and slowly examine surfaces from multiple angles. Years of experience allow them to recognize subtle visual patterns that automated systems occasionally miss. They look for tiny distortions in reflected light, imperfections that don't always match existing defect databases. In an age of robotics and artificial intelligence, the trained human eye remains one of the most valuable tools in the factory. Finally, approved windows receive documentation packages that trace every stage of their creation. Manufacturers record material origins, processing conditions, inspections, test results, and certification data. Years later, engineers can still identify exactly when and how a specific window entered service. Few products on Earth carry such a detailed history. At this point, the window appears complete. It is transparent, strong, certified, and ready for flight. But the story doesn't end inside the factory. Around the world, millions of these windows connect passengers to the skies every single day. The scale of that industry and the numbers behind it are far more astonishing than most people realize. Now step back and look at the bigger picture. Every year, the global aerospace industry produces hundreds of thousands of aircraft windows for commercial jets, business aircraft, military platforms, helicopters, and replacement fleets. Together, these transparent components form one of the most specialized manufacturing sectors in aviation. Most people see only a window seat. Behind it stands an international network of mines, chemical plants, factories, laboratories, engineers, and technicians spanning the globe. The market for aircraft transparencies, including passenger windows, cockpit windshields, cabin panels, and specialty aerospace glazing, generates billions of dollars in economic activity each year. Thousands of highly skilled workers dedicate their careers to producing, testing, repairing, and certifying these components. Imagine an entire industry built around creating something that people barely notice during a flight. That's the hidden power of modern manufacturing. Today, the United States remains one of the world's largest aerospace manufacturing centers. France, Germany, the United Kingdom, and China also play major roles through aircraft production, materials engineering, and specialized aerospace supply chains. Together, these nations account for a large share of the industry's technological development and manufacturing capacity. But here's what nobody tells you. A single aircraft window may involve suppliers from several different countries before final installation. 50 years ago, aircraft windows looked very different. Engineers worked with smaller designs, simpler materials, and far less computing power. Inspection relied heavily on manual measurements and visual judgment. Today, laser scanners, artificial intelligence, digital twins, and advanced materials science push reliability to levels that earlier generations could barely imagine. The evolution of aircraft windows mirrors the evolution of aviation itself, and the future may be even more remarkable. Researchers continue developing lighter materials, smarter coatings, improved scratch resistance, and advanced transparency technologies. Some concepts explore integrated sensors capable of monitoring structural health throughout the life of the aircraft. Others investigate new materials that could reduce weight while maintaining exceptional strength. Every kilogram saved helps airlines reduce fuel consumption and emissions. Did you know that passenger windows contain a tiny bleed hole designed to manage pressure between layers? Most travelers never notice it, yet that tiny feature plays a critical role in the overall design. Did you know that cockpit windshields can contain heating systems powerful enough to prevent ice accumulation during severe weather? And did you know that some aircraft windows experience thousands of pressurization cycles during their service lives while maintaining strict safety margins? Suddenly, that simple view of the clouds feels very different. Think about this. A passenger window may travel through multiple countries, survive intense heat, pressure, machining, polishing, testing, certification, and years of operation before retirement. Yet during every flight, it performs its job so quietly that most passengers never give it a second thought. That may be the greatest compliment any engineered product can receive. We began this journey high above the earth, staring through a small transparent panel while crossing the sky at incredible speed. Along the way, we followed hydrocarbons from deep underground, watched chemical reactions create aerospace materials, entered precision factories, and witnessed testing systems designed to push every component to its limits. What seemed simple at first revealed layer after layer of hidden complexity. And this is where manufacturing becomes something more than production. It becomes a story of human ingenuity. Every aircraft window represents thousands of decisions made by scientists, engineers, technicians, machinists, inspectors, and pilots. It carries the knowledge of generations who learned how to shape transparent materials into something strong enough to challenge the harshest environments in aviation. Most people never think about this. Yet every safe flight depends on countless components built with this same level of dedication. The next time you sit beside an aircraft window and watch the world pass below, you'll know you're looking through far more than a transparent panel. You're looking through decades of research, extraordinary manufacturing, relentless testing, and uncompromising safety standards. Hidden inside that clear view is one of the most remarkable engineering stories in modern transportation. The next time you hold one of these in your hands, remember, it didn't just appear. It was born from the earth, shaped by fire, perfected by technology, and approved by the strictest standards in the world. That's not just a product. That's a masterpiece of human engineering. If you want to go deeper into the Hidden world of manufacturing? Tell us in the comments. What product you'd like to explore next? Like this video, subscribe to the channel, and we'll see you inside the next factory.